My name is Bert Huang. I'm a professor here in the computer science department at Virginia Tech, and this is the first in a series of video lectures for the machine learning course. So in this video, I'm going to go over a high-level overview of machine learning. And to get started, it's useful to think about where machine learning fits in the modern economic landscape. So if you look at Glassdoor.com's list of 25 best jobs in America for 2015, you see that at number 9, they have listed data scientist. This is rather remarkable because the concept of a data scientist didn't really exist a few years ago, and it's really something that's cropped up over the past few years, partially because of the maturity of the field of machine learning and the explosion of data that has been appearing in various industrial contexts, where lots of people have started to realize the importance and the value in taking empirical data and using computers to analyze and guide decision making. So a lot of press has picked up on this and started writing articles about this to general audiences, and companies are starting to really take seriously the need for getting people who are good with working with data. And they're not completely sure exactly what they want sometimes. Sometimes they want, they know that they need a data scientist, but they don't exactly know what a data scientist is. In fact, a data scientist or data science in general is not very well defined. It's one of these things that lots of people have different definitions for depending on where they're coming from. So you can Google for it. You can try to figure out what the general consensus idea behind, what a data scientist is by searching on the internet. But a lot of times, what you find is things where people are essentially disagreeing about what they should be writing. So if you look at the Wikipedia article on data scientists, you'll see that uh, some of the Wikipedia editors have flagged it as an article that has, it says, a tone or style that may not reflect the encyclopedic tone used on Wikipedia. So this is a kind of a debated topic of what exactly data science is. So I can give you my definition, and essentially, like I said, it comes from where my background is, which is in academic research. So I come from the machine learning research area, and therefore my idea of what this very popular idea of data science is heavily influenced by that. So my view is that data science is roughly how one can use data to answer questions or guide decisions. So that's a very, very vague and high level definition. But data science is also easily viewed as a culmination of various research disciplines or scientific disciplines, and it comes from computer science and statistics. Essentially, those are the big high level areas, and then within computer science, um, I'm of the opinion that it comes from machine learning and data mining. So of course this class is on machine learning, and we're not going to talk as much about data mining, although of course these areas heavily overlap, so it's hard to really separate them out. But to me, machine learning is really at the core of what has made data science a relevant new idea. So machine learning is the idea of taking a computer and having it improve with experience at some task. Right? You give a computer some task, which we've been doing for decades since computers became popular tools to the general public. But the idea is that not only do we give it some task, not only do we write some program to have it solve some problem for us, we also give it lots of examples and lots of experience, and it gets better at that task. So to be precise, we like to specify exactly what the task is that we're going to be doing machine learning on, and how we're going to measure the performance of the computer at that task. So we're going to have some performance measure, and then we'll have some experience for the computer to learn from. That experience may be in the form of a huge data set, or maybe in the form of some environment where the computer gets to interact with the environment or make decisions in the environment, and then it gets some feedback. Right? That can be a form of experience. And another way of viewing machine learning is to think of it as this meta level computer programming. It's essentially like we're writing a computer program, that itself will write computer programs, and it improves that, or the computer program, the machine learning algorithm can improve its computer program output by getting more data or more experience. So with that somewhat established, we'll spend throughout the rest of the course. We'll refine that definition. We'll understand the caveats that come with it, and all the different variants of definitions of machine learning that exist out there. But with that general idea planted, the rest of this video is going to go into 3 specific machine learning success stories, and then I'll tell you one cautionary tale. And of course, there's many success stories and many cautionary tales, but it's important to have some examples to ground our discussion in. So then that cautionary tale is going to lead to a discussion of machine learning research, which is going to be the main focus of this course. So let's get on to the first of 3 machine learning success stories. So the first one I'm going to talk about is face detection and recognition. And this is one of those things that if you look at science fiction in the, I don't know, up until the past 10 years, this often comes up, that you would often have science fiction sort of creative people, whether they're authors or screenwriters or what, they come up with like this crazy idea that someday in the future computers will be able to look at a camera input, to look at an image or some video, and they'll be able to find the people in the video, and they'll be able to know who you are. And it seemed so far-fetched back then, that and fantastic, that it was this exciting idea in science fiction. But of course, now we know that we all have machines that can do this in our pockets, or at least most of us have smartphones that have face detection for autofocus. We have Google Photos now, lets you upload all your photos, and it separates all the different people in your photos into different categories, and it's really quite impressive. But it's taken over our everyday technology to the point where we don't even think about it anymore as anything special. But if you take a closer look, or take a step back from what how we've seen the progress happen over the past few years, it really is remarkable, right? You think about now, I mean, if you told somebody in 1995 that I would be holding a computer in my pocket that I can pull out, and it will find the faces in the image, and know to focus on those faces because that's what we care about when we take photos, that person would probably not believe us. At least I wouldn't have believed it back then. And part of the reason that it's hard to believe for someone in the past is it's hard to imagine how you program a computer to do that. Right? If you think about images in computers represent images as pixel values. They're essentially just numbers organized into a grid. Usually there's 3 numbers per pixel, so it's usually red, green, and blue values. And I guess you can, based on the configuration of the pixels, you can figure out what pixels are next to each other. And if you were to try to sit down and write a computer program that would look at an image and decide what part of that image is a face, it's pretty hard to imagine. I mean, you basically have to write something absurd like, pixel 425 by 556 should have this range of red values and this range of green values, and it's really something that you wouldn't be able to do. And even if we had to try to describe in English rather than computer language what a face looks like, that itself is also pretty hard. I mean, we can kind of do it, but if we didn't have hard coded into our genetics, the predisposition to learn how to recognize faces, it would be pretty hard to teach our children, our younger generations, how to recognize faces. I mean, you'd have to say, okay, well, a face is a round thing that usually is on top of a person's body, unless that person's upside down, in which case it's below it, and usually has 2 eyes, unless they're wearing sunglasses, in which case it has no eyes, or if they have an eye patch, they might have 1 eye. And there's a nose, but different people's noses look totally different from each other. So it's really challenging. But what modern face recognition systems do is they essentially take a similar approach to what we do as humans, which is they give a computer program lots and lots of examples of images of faces. So these examples are, again, just like I said before, are images, digital images. So they're described by lots of numbers organized into pixel values with red, green, and blue intensities. And then they also include lots of examples of things that are not faces, right? So on the top we have lots of faces, and on the bottom we have lots of non-faces. And the computer program is designed to separate out these high-dimensional numbers. It basically just says, okay, well, here's a batch of numbers that are faces, and here's a batch of numbers that are not faces. And how do we mathematically separate out these numerical, high-dimensional vectors? And right, so the computer ingests all the data and outputs some really complex computer program that we would never be able to write by hand, right? As a human, the best programmer in the world would probably never be able to write this kind of thing out. So this technique, right, is machine learning, right? We basically say, here's a computer program that's going to be to learn from data. We give it the data, and it just happens to be that the data is faces and non-faces, right? It could have been anything else. It could have been cats or non-cats. So it's one of the famous examples that Google recently, showed they could develop a really, really accurate cat detector. Right? You could do anything because the computer program doesn't care. It just sees a bunch of computation or numerical representations of objects and numerical representations of other objects, and it tries to separate those two numerical representations. And what you get when you do this type of machine learning is really impressive results. So here's a video I downloaded off of YouTube where somebody just downloaded an open source face detector, ran it on, I guess, I don't actually know what data set they ran on, but they ran on some data set that separates faces from non-faces, and then you can run it on this video, and it actually is they're able to run in near real time and separate out faces in this scene from the Matrix. Now, you actually see a bunch of errors that the classifier makes. For example, it doesn't see Morpheus's face, or rather, it doesn't realize Morpheus has a face because Lawrence Fishburne's face is turned too far at an angle that perhaps wasn't represented in the data set. Or maybe the sunglasses are confusing the classifier. But regardless, it's still doing a really impressive job at this task. So that's face recognition, and it's one of these examples where right, this technology is made possible by machine learning, and it's become ubiquitous. It's in all our smartphones. It's in a lot of our online services like Facebook and Google, and it's really become part of our lives. Okay, so the second machine learning success story I'd like to talk about is recommender systems, and this was a really exciting and newsworthy topic a few years ago when Netflix had their famous Netflix Prize competition. So what they did was they released a huge data set, or at least huge for that time, data set of anonymized users and which movies they liked, or what ratings they gave to a huge collection of movies. And what they said was, we're going to release the data, and in 2 years, I think it was 2 years, that they're going to say who has the highest accuracy prediction. Whoever has the highest accuracy prediction for what people will rate different movies will win $1 million. And so they invested $1 million to get the entire academic scientific community working on their data. Of course, now in the modern landscape, there's a website called Kaggle where people are uploading data and running competitions all the time. The prizes are a bit smaller than Netflix, and the number of people working on it tends to be a bit smaller than Netflix, because Netflix was really a pioneer in this idea of a competition, this sort of competition. But aside from the contest story that went along with this, the actual problem that they're looking at is a really interesting one in machine learning, because it turns out that, right, if you think about the landscape of different companies interested in doing machine learning nowadays, recommendation is as a rule of thumb, the main thing everybody wants to hire people to do, right? They want to improve people's user experiences in online services by figuring out their preferences and providing them with what they want. Right? In the Netflix example, it's that if you are signed up for Netflix, they want to be able to recommend you what movie or what TV show to watch next, so that you keep coming back to Netflix. Right? You don't want to have a situation where you go to Netflix and you don't see anything you want, and then the recommendations are not very good, and you just say, okay, well, I'll just do something else instead of watching Netflix. And then a few weeks later, you say, well, should I pay my Netflix bill or should I cancel my service because I don't really watch Netflix anymore? Right? That's the worst thing that these companies can imagine, is that if you don't get good recommendations and you no longer enjoy the service, you're going to cancel the service. Or for free services, if you stop going to the website, you're going to stop being shown advertisements, which is what the advertisers pay for. So there's lots of examples of recommendation going on in our modern technological ecosystem. So there's recommendation for music, there's friend recommendation on social networking services, and there's product recommendation on online marketplaces like Amazon. And a lot of these work in a very similar way. So basically what you get is you get a lot of data from people who have previously interacted with certain objects. So for example, if we're doing movie recommendation, maybe you have the ticket sale records from two users. You have Alice and Kathy, and Alice over the summer saw Inside Out and Minions, and Kathy over the summer saw Terminator Genesis and Jurassic World. So the problem of recommendation is when you get a new user, let's say Barbara shows up, and you see that Barbara saw Inside Out. So now you want to recommend another movie for Barbara to watch. And based on the data, right? We of course this is a cartoon example where there's a tiny data set, but in this tiny data set, if a good machine learning algorithm would probably identify that there's two types of people. There's Alice people and there's Kathy people. And Alice people like animated films like Inside Out and Minions, and Kathy type people like action movies like Terminator and Jurassic World. So Barbara saw Inside Out, which means Barbara's probably an Alice type person, right? So that means Barbara will likely enjoy another animated film like Minions. So you might recommend Minions. And if you look at the paper written by the people who actually won the $1 million Netflix prize, they show this image here where they say that the machine learning algorithm actually learns numerical representations of different attributes of movies. And it's multidimensional, but they show here only two dimensions. They show that the movie could be either serious or escapist, or they could show that the movie was geared toward females or geared toward males. Now, in reality, the numbers that come out of the machine learning algorithm they used for their method don't actually have these interpretations, or they don't necessarily have these interpretations. Humans look at the numbers that come out afterwards and maybe can put these interpretations on, but to the computer, to the machine learning algorithm, these are just numbers. These are just unidentified numbers that characterize some feature of movies and of users that you can use to decide which sort of movie type a user is more closely connected to. So the gender-based stereotyping of movies and users is really something that the authors put in for this cartoon image, as opposed to the machine learning algorithm identifying. So the third machine learning success story I'd like to talk about is something that's very closely related to our university. And it's this project that's come out of the computer science department and a few other universities, or a few other researchers at other universities, called the Embers Project. And the goal of this project was to predict the news with social media data. So this is an ongoing project led by Professor Naren Ramakrishnan in the computer science department at Virginia Tech. And the goal of this project is to take information that's openly accessible on the internet, and use that information to try to predict newsworthy events. So just like we have journalists reading Twitter, trying to figure out if there's protests going to happen, or figure out if people are tweeting about an earthquake that just happened that the major media hasn't picked up on. We want computers to do that too. We want computers to do that, especially, and computers would hopefully be better than humans at doing this, because the amount of social media data out there is rather large. So an example of this is that maybe the computer program would be constantly looking at Twitter, and looking at all the structured information inside Twitter data. So you have things like geolocation, and you have information about the user who tweeted the tweet, or what device they're tweeting from. All that information is all publicly accessible for public tweets. And to take that information and try to figure out things like whether they're complaining about some political issue, whether they're planning a political protest, or whether there is a protest going on and they're tweeting about an ongoing protest. So, so this is an example of where machine learning can be used in a very interesting way, because the type of data that's being considered is really multifaceted and has a complex structure. Right? So Twitter is not just a bunch of you know uh, images of faces or anything. It's actually, right, there's this complex network of people talking to each other, communicating, either broadcasting in a general tweet or talking specifically to each other if they're communicating on social media toward other users. So so the system that the team has built is able to predict whether a protest is going to occur a few days in advance. Essentially, it can pick up on when people are complaining, or when people are transitioning from complaining to planning an actual protest. And to accomplish this, it requires analysis of the vocabulary of civil unrest, the message patterns that occur before each of these types of events, and maybe the geospatial distribution of these types of tweets that are signals of these upcoming events. So the three success stories I've talked about are face recognition, which is pretty much ubiquitous; recommendation, which I think is also ubiquitous but not as successful, because if you think about all the services that we use every day, they're not particularly good at recommendation, right? We log on, and we a lot of times what it recommends aren't very good. Whereas with face detection and face recognition, those are really, really good. And it's, they can be improved. They're not always perfect, but it's hard to imagine them improving much. Whereas with recommendation, they can improve a lot. And then I talked about news event prediction, which is a really, really hard problem. And there's a lot of active research going on here at Virginia Tech and all over the world in different research labs on how to do that. But overall, these three stories all represent things that machine learning has done reasonably well at, and where machine learning is, a tool that we probably should continue using. But not every use of machine learning is successful, and the one uh, cautionary tale I really wanted to highlight is the story about the economic collapse of 2008. So this economic event, if it can really be characterized as a single event, has affected all of our lives rather significantly, perhaps more significantly than any other occurrence that's happened in our lifetimes. Um, and one of the reasons that analysts cite for this collapse is the use of a particular statistical formula that became very, very popular in financial analysis, but was never, or was not fully understood by the people who were using it. So there's an article posted about this that says that there's a formula in statistics misunderstood and misused has devastated the global economy. And this is a formula that it's not really important what it is, but it turns out it's something called the Gaussian copula. Um, and it's essentially a fairly new idea, at least relative to other statistical ideas, that that there's still lots of active research on. But it worked really well at first. So a lot of financial experts started really picking up on this and using it for their modeling, and they were doing this without full understanding of how it worked, um, or full appreciation of how new an idea it was. So what happened was, this led them to predict things that were, well, to put it lightly, they were very wrong. They made predictions that were inaccurate, and then they made recommendations to people to buy or sell stocks, or I don't actually know economics that well, but they made some sort of decisions based on these models that led people down the wrong path and created a bubble that burst and was devastating to the economy. So that brings me to the importance of machine learning research. So, right, we're not at the point with machine learning where we can say, oh, machine learning works. Right? Machine learning doesn't necessarily work. We don't know if it works. We know that there's a bunch of examples where it works pretty well. But as a computer scientist, as someone with a skeptical mind, I always want to understand, when is it not going to work? And it's not just a scientific curiosity. This is really an important engineering decision and practical consideration, which is that if we think of it as think of machine learning as just a discipline where we can throw in data and make awesome predictions and go out in the world and make lots of money, then, well, clearly that's not true. And if we make the assumption that it is, we could find ourselves in a lot of trouble. So research essentially tries to understand the limitations and the capabilities of machine learning. So the questions we like to ask in machine learning research are, how do we know if the models we learn are good, or how do we know if they're going to be fair, when applied in practice? How do we learn from lots of data efficiently so we don't end up with situations where all of a sudden we have too much data and it's too expensive to run the machine learning algorithm? And how do we learn about more complex ideas like natural language, social networks, or biology? So the last bullet is where my personal research tends to live in that space. So I'm going to talk about that very briefly so you have an idea of where I'm coming from as I teach this course. So I'll give you an example of a problem. So suppose you want to understand the political preferences of users as they visit different news websites. Okay, so you often see people commenting on websites, and sometimes it's hard to tell. Occasionally, it's hard to tell whether they're agreeing with an article or disagreeing with an article, and a lot of times one of the clues is what news service has posted the article. So if it's Huffington Post, then at least from my experience, it's typically a liberal viewpoint, and then if it's Fox News, it's typically a conservative viewpoint. But maybe you see something where a user on the website posts a comment, "Thanks, Obama," right? And you don't know if they're being sarcastic or not. And I guess my guess would be they're being sarcastic because that's the typical, more common usage of "Thanks, Obama." But then you also get maybe other information from other users who are interacting with the first user. So Jane Doe originally posted "Thanks, Obama," and then John Smith 3 then posts in response to Jane Doe, haha, right? And right, this is just a single two-person interaction, but it gives you a lot more information than just the original post by itself. It sort of suggests that probably Jane Doe 1 was joking, assuming John Smith 3 was accurately interpreting the sarcastic tone, or furthermore, you might gather more information by whether John Smith 3 and Jane Doe 1 are friends on Twitter, right? You might look at their social network connections, and if they are friends, then there's a higher chance that John Smith properly interpreted Jane Doe's tone. But But okay, so this is just an example of a two-person interaction. But when we get to social media as a whole, viewing it in as a big picture, you have a much more complex situation where there's lots of different connections, lots of people responding to different people. In patterns and sometimes cascades of information, right? Where somebody posts something and then that person's friends retweet it or repost it, and then the friends of friends repost it. You see these sort of cascades of information flowing, and you get these very complex patterns of information, right? The data ends up being very, very complicated. It's hard to visualize. Here's an attempt to visualize something like a social network, but it's actually quite a that's actually an area of research how you do it. And my research aims to think about these situations. My goal is to understand machine learning in these settings, understand what machine learning is capable of, and how we can come up with new machine learning algorithms that can handle these situations. So, right, many applications have complex structure that traditional machine learning tools can't handle exactly, so we need new algorithms and new theory, and that's the basis of my research. So that should give you an idea of where I'm coming from as a machine learning researcher. And then just to go back to the course, the goal of the overall goal of this course, right? It's an introduction to machine learning, but it's a little bit different from other courses you might take in, say, data analytics or statistics. In that, my goal is to teach you the science and research of machine learning, or the foundational tools that you need to do science and research in machine learning. So that means you're going to need to understand, or you're going to learn over the course, the mathematics and theory behind the methods. And it also does, in some pragmatic sense, mean that we're going to spend less time on looking at things like software packages for machine learning. Right? We're not going to even touch things like really popular software packages like scikit-learn for Python. We're not going to talk about that at least much over the semester, because it's at least I'm of the opinion that if you know the foundation, if you understand these algorithms from a computer science perspective or a mathematical perspective, then you will easily pick up on the software side of things. And the course will be done in a flipped format, which means there's going to be video lectures like the one you're watching now. You're going to watch these lectures, and then in class we're going to solve problems or have discussion or work on some of the homework together in the class. And the goal of this format, at least from my view, is that I want to minimize the amount of time in class that I'm just spewing information at you, right? I don't want to spend class sessions going over slides in a one-way interaction. I'm hoping that we can make class more interactive so that you get more of the benefit of being face-to-face with me, whereas I can give you lectures online, and then you can even pause and rewind and watch them at your own pace. So with that said, go ahead and watch the other two videos I posted for the second session, and we'll be able to discuss them in class.